Today, we're going to be looking at section 5.4, which is about sampling distributions and the Central Limit Theorem. Now, before we get deep into this section, and this section is deep, understand that the Central Limit Theorem is a fundamental principle by which we will be doing a lot of things from this point forward. So it is of incredible importance that you pay very close attention to what's going on here. Sometimes it's not going to seem like some of the stuff makes sense, and that's why if you look at your pre-printed notes, a lot of this is pre-printed. So there's not as much for you to write in as you would in a normal set of notes. I just kind of want you to listen and watch and do some stuff sometimes, but for the most part, there's not a lot for you to do here. So we really start with a question. Have you ever wondered how statistics really works? One of the times that we see statistics in all of its glory is during election season. And so every time we have an election in this country, there's always media coverage of the results. Okay, right? People at polling places. The news agencies report results as soon as they get them. And most of the time, they get updated results as precincts close. They tally their votes and report their data. That's when statistics really comes to the forefront. The true wonder of statistics is all the cool stuff that we get out of it. News agencies begin predicting winners. And oftentimes when they're making these predictions, there's only 5 to 10% of the precincts reporting. Now, that means that 90% of all of the precincts, probably about 90% of all the votes, haven't even been counted yet. But they still make the prediction. It seems like a recipe for disaster, right? That there's going to be a lot of inaccuracy if you're saying, okay, here's a 9% of the vote, and I'm going to say, oh, this is the winner, when 91% of the vote hasn't even been counted. But the amazing stuff that happens is that on election night, the predictions that they make are about 99% accurate. Amazing but true, right? So how does it work? Now, we say 99% accurate because it's not always accurate. You can think back to situations in recent history. In the year 2000, when George W. Bush and Al Gore were running for the presidency, there was a moment in time where they declared Al Gore the winner of the Florida primary, which would give him enough votes in the Electoral College to win the presidency. But then half an hour later, they had to walk that prediction back and say that it was too close to call because they made a prediction with a small number of precincts. And then as more precincts were reporting, they realized that the numbers didn't hold up. So then they couldn't call the winner of that state. You can also see more recent polling in 2016 when Donald Trump and Hillary Clinton were trying to become president of the United States. And all the polls consistently showed Hillary was going to win, Hillary was going to win, Hillary was going to win. And then on election night, Donald Trump ended up winning. Even though Hillary got more of the popular vote in the Electoral College, which is all that really matters in the run for the presidency, Donald Trump got more delegates to the Electoral College. So a lot of times these predictions that they make are accurate, but there are instances where they do fail. But we still want to know how it works. So what happens is they take samples from a population, and they do it over and over and over again. So let's say they're going to take samples of size 50. They take a sample of size 50 from the population, and then they figure out something about that. And they do it with replacement, which means then they throw all 50 of those people back in the hat, and they draw another sample of size 50. And some of those people who were in the first sample could be in the second sample. Some will not be, right? So you're going to do this over and over and over again. And because you're doing it with replacement, there's an infinite number of possible samples that you can get. Because you can just keep pulling them out, pulling them out, pulling them out. There's no end. If we did it without replacement, we would eventually run out of people. But because we're throwing them back in, we can always get another group. Once we do that, we look at each sample and we find the mean for each sample. And then those means become your data values. And when we use the means of samples as our data values, that is called a sampling distribution. So here's our definition for a sampling distribution. It's a probability distribution of a sample statistic that is formed when samples of size n are repeatedly taken from a population. So we have a little diagram here. I like this diagram. Did it myself. That's why I like it. What we see here is samples being taken from a population. And you'll notice that each sample that we're taking has its own mean. So sample 1 has x bar 1, sample 2 has x bar 2, sample 3 has x bar 3. And some of those samples are overlapping because we're doing it with replacement, right? So we pick a sample out, we record it, we throw it back, all those individuals back in, and then we pull the next sample out. So some of those individuals from one sample might also be in another sample, or in several other samples. Right? I only did a few samples here, I only did 9, but it would be possible to do, 100,000 samples from the same group. And then you'd have a lot of overlap. So when you have a situation like this with the sample statistics and you're finding their mean, when the sample statistic is the mean, we call that the sampling distribution of sample means. So we've got an example here. Imagine that you wrote the numbers 4, 8, 12, 16, and 20 on slips of paper and placed them in a hat. Those 5 numbers make up your population. You draw out a slip, record the number, and put the slip back into the hat. After mixing the slips well, you draw another slip and record the number. This is drawing with replacement. Okay. So what we want to do is a few different things. We want to find the mean and the standard deviation of the population. We want to list all samples of size 2 from the population and calculate the mean of each one of those samples. Then those means that we get, those x bars, we want to let them be our new data values, and we want to find the mean and standard deviation of this set. And then we're going to compare those values that we get in part C to the population values that we got in part A. So let's look at our solution here. We have to find the mean of those 5 numbers, 4, 8, 12, 16, and 20. So we add them up, 4 plus 8 plus 12 plus 16 plus 20, and those add up to 60. 60 divided by 5 is 12. So the average, the mean of those 5 numbers is 12. If we're going to find a standard deviation, we can construct a table, right? We did that back in section 2.4 when we were talking about standard deviation. We would list each data value, 4, 8, 12, 16, and 20, and then we would find their deviations. You would take the data value minus the mean. So the data value 4 minus the mean of 12, 4 minus 12, is negative 8. Then you do the same for 8. 8 minus 12 is negative 4. 12 minus 12 is 0. 16 minus 12 is 4. 20 minus 12 is 8. Then we're supposed to square the deviations because we want to get rid of the negativity. So negative 8 squared is 64. Remember, when you square, you should get positive numbers. Negative 4 squared is 16. 0 squared is 0. 4 squared is 16. 8 squared is 64. Once we've got that table filled out, we can go to the formula for the standard deviation. The formula for the standard deviation says that, we'll start with the variance. We take those squares of the deviations, we add them up and divide by the population size. So that's 160 if you add that last column. 64 and 16 make 80. That happens twice, and then the 0. So you got 2 80s and a 0, which is 160. You divide it by 5, and you get 32. That's the variance. The standard deviation is the square root of the variance, so it's the square root of 32. And the square root of 32, if you write it in radical form, now if you plugged it into your calculator, you would get something around 5.6-ish. But if we write it in radical form, we'll be able to see a pattern that comes out at the end. So that's why I wrote this as 4 square root of 2. So our sigma here is 4 root 2. Now, in part B, because we're looking at drawing with replacement, there's 25 different possible samples. Okay? These are those. So with replacement means we draw a number out, we record it, we put it back, and it's eligible to be drawn again. So that first sample that we have listed, 4, 4, we draw out the 4, we record the 4, we throw the 4 back in the hat, we mix it up, we draw the next number out, and we get the 4 again. That's possible. So we get 4 and 4, 4 and 8, 4 and 12, 4 and 16, 4 and 20, 8 and 4, 8 and 8, 8 and 12, 8 and 16, 8 and 20, 12 and 4, 12 and 8, 12 and 12, 12 and 16, 12 and 20, 16 and 4, 16 and 8, 16 and 12, 16 and 16, 16 and 20, 20 and 4, 20 and 8, 20 and 12, 20 and 16, 20 and 20. Okay. So we get each one of these pairs. We find the mean for each one of those pairs. We do that by adding the two numbers together and dividing by 2. So 4 plus 4 is 8. 8 divided by 2 is 4. 4 plus 8 is 12. 12 divided by 2 is 6. 4 plus 12 is 16. Divided by 2 is 8. Here we get 10. Here we get 12. Then with the 8s, 8 plus 4 is 12. Divided by 2 is 6. 8 and 8 is 16. Divided by 2 is 8. 8 and 12 is 20. That gives us 10. 24 gives us 12. 28 gives us 14. Then 16 gives us an average of 8. 20 gives us an average of 10. Then an average of 12, 14, and 16. Then we've got an average of 16 and 4 gives us 10. 16 and 8 gives us 24. Divided by 2 is 12. Then 16 and 12 gives us 14. Then 16. Then 18. 20 and 4 give us an average of 12. 20 and 8 an average of 14. Then an average of 16. An average of 18. And an average of 20. Okay, so that's part B. All part B wanted us to do was list all of the samples and find their means. Part C, we want to try to find the mean of the means. And then once we do that, we'll find the standard deviation for that data set as well. So with the mean of the means, we're going to introduce this new notation. This notation right here, mu of x bar. Okay? This mu of x bar means that we're finding the mean, that's what the mu is, of the x bars, of the set of means. So this is really a mean of means. We take all of the means that we just found, we found 25 means, and we find their average, and that's the mu of x bar. Okay. So what we see here is a table, and I've listed all of the different sample means that we got. We got 4, 6, 8, 10, 12, 14, 16, 18, and 20. Some of those means occurred more than once. So if we also incorporate their frequency, then we can deal with a smaller table. This is much smaller than listing all 25 values and getting repeated values in the table. So the sample mean of 4 came up just one time. 6 happened twice, 8 happened 3 times, 10 happened 4 times, and 12 happened 5 times. 14 only happened 4 times, 16 happened 3 times, 18 happened 2 times, and 20 happened just once. We can use those x bar values along with the frequency. We multiply them together, And then if we add up that column and divide by the 25, we'll find the mean. So 4 times 1 is 4, 6 times 2 is 12, 8 times 3 is 24, 10 times 4 is 40, 12 times 5 is 60, 14 times 4 is 56, 16 times 3 is 48, 18 times 2 is 36, 20 times 1 is 20. Okay, so now what we do is we're going to add up all of those numbers in the last column. They add up to 300. And we divide by 25 because we had 25 of those means. So 300 divided by 25 is 12. That's our mu of x bar. Okay. So now what we can do is we can build a table just like we did in the first part when we were finding the standard deviation of the 5 numbers. Now we're going to find the standard deviation of all of these means. And now what we're going to see is our formulas change a little bit. They don't change in structure. They just change in the way they look a little bit because we've got some new notation. So we repeat the table that we were just looking at where we have each one of the sample means, its frequency, and then the mean times the frequency. And then in our next columns, instead of x minus mu, we've got x bar minus mu of x bar. The reason that it changed is because our data values aren't x's anymore. We started with x's. Those 5 numbers were the x's in the beginning of the problem. What we found, we're looking at x bars, which are the averages of these pairs. So it's x bar minus mu of x bar, right? These are still deviations, right? A data value minus the mean, it's just now the data value is a mean itself, and the mean we're finding is the mean from the set of means. So instead of x minus mu, it's x bar minus mu of x bar. But the idea is the same. That's a deviation. And then once you find the deviation in the next column, you have to square it. That's not changing. And then because we're using the frequency distribution here, we have to multiply the square of the deviation by the frequency f. All right, so we just said that mu of x bar was 12. And so we have to take our sample mean, the x bar, minus the mu of x bar. So for the first row, it's 4 minus 12, which is negative 8. Then we've got 6 minus 12, which is negative 6. 8 minus 12, which is negative 4. 10 minus 12, which is negative 2. 12 minus 12, which is 0. Then 2, 4, 6, 8. For the next column, we're going to square. And remember, whenever you're squaring things, those answers are going to come out positive. So negative 8 squared is 64. Negative 6 squared, 36. Negative 4 squared is 16. Negative 2 squared is 4. 0 squared is 0. 2 squared is 4. 4 squared, 16. 6 squared, 36. 8 squared, 64. Now we're going to take each one of those squares in that column and multiply them by the frequency. So in the first row, we've got a frequency of 1 times the squared deviation 64. 1 times 64 is 64. Then in the next row, 2 times 36 is 72. In the following row, 3 times 16 is 48. 4 times 4 is 16. 5 times 0 is 0. 4 times 4 is 16. 3 times 16 is 48. 2 times 36 is 72. 1 times 64 is 64. So if we added all these numbers up, they actually, in that last column, they actually add up to 400. Okay, so that's going to help us when we go to find the variance in the standard deviation. So if we find the standard deviation, which is sigma of x bar, it's the square root of, this is really the same standard deviation formula we've been working with. It's just now we have that x bar, mu of x bar notation in it for our deviation. So it says add up all of the squared deviations times their frequencies, and then divide it by the total frequency. We just said it was 400, and then the sum of the frequencies is 25. So 400 divided by 25 is 16, and the square root of 16 is 4. So we had a mean of 12 and a standard deviation here of 4. Notice the difference of the standard deviation notation. It's not just sigma, it's sigma of x bar. That's relating to us that this standard deviation is the standard deviation of a set of means. Now we can compare the data values. First thing we notice is that when we found mu of x bar, it was 12. When we originally found the mu, it was 12. So mu of x bar was equal to mu. That's actually always true when we're dealing with sampling distributions of sample means. The other thing that might not be quite so easy to see is the relationship between sigma that we found, which was 4 root 2, and this sigma of x bar, which was 4. So sigma of x bar is 4. Another way to write that is 4 root 2 over root 2, because the root 2's would cancel. 4 root 2, remember, was sigma. And the square root of 2 is the square root of n, because we took samples of size 2. This is our relationship here. So sigma of x bar ends up being sigma, the population standard deviation, divided by the square root of the sample size. That's also always true. Okay, so that's a lot to digest, right? So we're going to summarize these statements right now in what's called the sampling distribution of sample means. So if we go through a set of data values and we take these repeated samples and we find the mean of the sample means, it's always going to be equal to the population mean. So that means that mu of x bar is always going to equal mu. And then for the standard deviation of the sample means, it's always going to be the standard deviation of the population divided by the square root of the sample size. So sigma of x bar equals sigma divided by the square root of n. So once you've got that under control, and again, this is a lot to digest, we're ready to explore probably the most important concept that we're going to see, which is something called the Central Limit Theorem. Now, the Central Limit Theorem has two parts. The first part deals with when does it apply. Okay, when can we use the Central Limit Theorem? And so there's two conditions, and you don't have to meet both conditions. It's either or. So if you meet the first condition, great, the theorem applies. If you don't meet the first condition, but you meet the second condition, great, the theorem applies. But you have to meet at least one of the two conditions. So the first condition is whenever the sample size is greater than or equal to 30 from any population, the sampling distribution of sample means approximates a normal distribution. And the larger the sample size, the better that approximation is. So bigger samples are better, right? We've seen that small samples can skew results. Big samples get us values that are way closer to the true values. Second condition is if the original population that we got our data values from was normally distributed, then when I go and find all those means, that sampling distribution of sample means will also be normally distributed, no matter how big the sample size is. So in part one, we don't know whether the original population was normal or not. And it doesn't matter because the sample size was big enough. But what the second condition says is that it doesn't matter what size the sample is if you know the original set of values that you were finding the means from was actually normally distributed itself. So if either one of those conditions are true, then the Central Limit Theorem applies. So the part two of this is, what does the theorem actually say? Well, what it says is that if the original population has a mean of mu and a standard deviation of sigma, then when one of the above conditions is satisfied, the sampling distribution of sample means has the following properties. The mean is mu of x bar, and that's going to equal mu, which is the population mean. For the variance, you have sigma squared of x bar will equal sigma squared over n. And for the standard deviation, sigma of x bar will equal sigma divided by the square root of n. So the central limit theorem just basically locks in those ideas from the sampling distribution of sample means. Now this value that we see at the end, this sigma of x bar, it has another name. We call that sigma of x bar value the standard error of the mean. The standard error of the mean. So, what is this all about? Okay. Well, up until now, when we've been asking probability questions, we've been asking probability questions about individuals. What's the probability that one of these things does this? You know, when we were talking about newborn babies, what's the probability that we find a newborn baby that's in this height range? What central limit theorem questions are is they're asking about probabilities not of a single individual, but of a group of individuals, right? So the central limit theorem allows us to talk about probabilities of groups of individuals, not just single one-off individuals. So the probability formulas that we're going to use are pretty much the same as what we've seen before. Our z-score formula, remember it was x minus mu over sigma. Now because of the notational changes where we're talking about the sampling distribution of sample means, instead of x minus mu over sigma, it's x bar minus mu of x bar over sigma of x bar, but we still find the z-score the same way. We still use the table the same way. Those things aren't different. Okay, so let's look at an example. Our example is about newborn babies. I have a lot of examples in the various sections that we talk about in the book about newborn babies. Maybe it's because I love babies so much. All right, so let's take a look at the example here. The length of newborn babies is normally distributed with an average of 19.4 inches and a standard deviation of 1.6 inches. Find the following probabilities. So, if a newborn baby is selected at random, just one, what's the probability that his or her length is greater than 20.04 inches? Second, if a group of 36 newborn babies is selected at random, what is the probability that the average length of the babies is greater than 20.04 inches? Notice the difference in these two questions. The first question is talking about one single baby. The second question is asking about a group of 36 babies. So this is the difference, right? Part A is going to be a straightforward probability question like the ones we've been doing in previous sections. Part B, though, is going to have to use the central limit theorem stuff because now we're talking about probability for a group. Whenever you're talking about probability for a group, that's when you're looking at the central limit theorem. Okay, so let's start with part A. This is just like the ones we've done before. We have to find the z-score. Remember that our x value here is 20.04. So z is x minus mu over sigma. Notice no notational switches here because this is not about the central limit theorem. This is just about one baby. So it's the regular x minus mu over sigma. The x was 20.04. The mu was 19.4. The sigma was 1.6. So 20.04 minus 19.4 divided by 1.6. Well, that's going to be 0.64 divided by 1.6, which is 0.40. So then this is the z-score. We're going to look up the z-score on the standard normal distribution table. So if you don't have that table out, Remember all the sections in Chapter 5 and in Chapter 6, we're going to need that standard normal distribution table. So if you haven't gotten it out already, go ahead and get it out. And we look up the 0.40 on the standard normal distribution table, and we find that value. The z-score of 0.40 results in a table value of 0.6554. Now, the table value, remember, is area to the left. This question asked, what's the probability that the baby has a length greater than 20.04? When we talk about greater than, that's area to the right. The table value is area to the left. So to compute the actual area, we have to do 1 minus. So the probability that x is greater than 20.04 is the same as the probability of z being greater than 0.40, which is 1 minus 0.6554, which is 0.3446. Okay. That's part A. For part B, now we're dealing with a group. This is a central limit theorem question because it's dealing with a group, and the group is bigger than 30, right? Remember, we had two conditions. Either we had to know the original population was normally distributed, or we had to know that our sample was size greater than 30. A sample of size 36 is definitely greater than 30. So we need to compute the values from the central limit theorem. We need to know what mu of x bar and sigma of x bar are. Well, mu of x bar was the same as mu. So mu was 19.4, mu of x bar is 19.4. Sigma of x bar is sigma divided by the square root of n. So because the sigma from the original problem was 1.6 and the size of the sample was 36, the square root of 36 is 6. So the sigma of x bar is 1.6 over 6. That does reduce, but we don't really need to reduce it at this point because we're just going to use it to make a calculation here. So my z-score formula now is the altered version. It's not the x minus mu over sigma, it's x bar minus mu of x bar over sigma of x bar. And so x bar, the average that we're looking for is this 20.04 minus mu of x bar, remember, is just mu, so that's 19.4, divided by sigma of x bar, which is 1.6 over 6. So we've got a fraction where the denominator is a fraction. So that's going to bring up some interesting things. When we subtract on top, 20.04 minus 19.4 is 0.64. To divide it by a fraction, you're going to turn that fraction upside down and multiply. So instead of dividing by 1.6 over 6, we're going to multiply by 6 over 1.6. So we take the 6 times the 0.64 on top, and the 1.6 stays on the bottom. And when we multiply that all out, we get 2.40. That's the z-score. So when we find the z-score, we're going to use that to find the table value. And again, this is still greater than, this is still area to the right. So we're going to have to, when we find that table value, do 1 minus the table value to find the actual area and probability. So you look up the 2.40, the table value is 0.9918. But to find the probability, we're going to do 1 minus the 0.9918. And that's going to be 0.0082. Look at the stark differences between the answers for Part A and Part B. They really asked a very similar question. You know, what's the probability of having a length over 20.04? But in Part A, we were asking about one baby having that length. And in Part B, we were asking about 36 babies having an average that was greater than that length. So if we interpret our results here, what does Part A tell us? Well, it shows us that there's a 34.46% chance that a single newborn baby will be more than 20.04 inches. 20.04 inches is long for a baby. Most babies are between 18 and 19 inches. So this is pretty long. What part B shows us, though, is that there's only a 0.82% chance that a group of 36 newborns will have an average length more than 20.04 inches long. So 34.5%-ish probability that one baby can get that long. One baby chosen at random will be that long. But what this is saying is that if I picked 36 babies at random and found the average height, there's only a 0.82% chance, less than 1% chance, that the average height will be more than 20.04 inches. And that brings us to a little bit of a note here. And what the note says is that it's harder for a group of data values to have an average value far away from the mean than it is for an individual data value to be far away from the mean. So one data value escaping from the mean, right? One baby being a little bit tall, that's not that hard. But for a group of those babies to be that tall, to have an average length that tall, that's very hard to do. You can see that when you look at a bell curve. Okay. When you look at the bell curve of a normal distribution and its sampling distribution, one thing always sticks out. And the curve from the sampling distribution of sample means is always taller and tighter than that of the population. Okay? So the big, tall, skinny one is from the sampling distribution of sample means. And that's because when you look at the formula for the standard deviation that says it's sigma divided by the square root of n, well, n is always going to be at least 2. You're never going to have a sample of only 1, so you're going to be dividing by some number. So the standard deviation for the sampling distribution of sample means has to be smaller than the standard deviation for the original data, because the standard deviation for the sampling distribution is sigma divided by the square root of n. Dividing by the square root of n is going to make it smaller. When you make the standard deviation smaller, then all those data values get more tightly packed around the mean, and you get a much taller distribution. So, earlier, we made the assertion that the larger the sample size, the better the approximation. Why is this true? And it has to do with what I was just talking about with the standard deviation. As n gets larger, the bottom of the fraction for sigma of x bar gets larger. This means the value of the fraction decreases. The bigger the number on the bottom of a fraction is, the smaller the value of the fraction is. So remember, this fraction represents the standard deviation for that sampling distribution of sample means. And so the bigger the sample, the smaller that standard deviation is. So the data becomes more and more tightly packed around the mean. The bigger the sample size, the more tightly packed in that data is around the mean. And that makes it even harder for a group of data values to have a mean far removed from the population mean, because we still have the empirical rule, right, that says that 68% of data values have to occur within one standard deviation of the mean, 95% within 2 standard deviations, 99.7% within 3 standard deviations. Well, if we're shrinking the size of the standard deviation, then that means more and more data values are closer and closer and closer to the mean. Okay, so we've got a practice problem. And this practice problem deals with vanilla ice cream. That sounds delicious right now. The cost of a gallon of vanilla ice cream is normally distributed with an average cost of $4.49 per gallon and a standard deviation of 45 cents per gallon. Determine the following probabilities. If a gallon of ice cream is selected at random, what is the probability that the price is between $4.22 and $4.85 per gallon? And then secondly, if a group of 16 gallon-sized containers of ice cream is selected at random, what is the probability that the average cost of the gallons is between 422 and 485? So the same question as part A, but now we're talking about a group of 16 gallon-sized containers of ice cream instead of just one. And there's a further question. Does the central limit theorem even apply? Remember that the central limit theorem had conditions, so we're asking, does this situation meet the conditions for us to be able to use the central limit theorem? If it doesn't, then say it doesn't apply and explain why. If it does apply, then go ahead and find that probability. So give yourself a little time to work that out and hit pause on the video. And when you're ready to hear the answer, just hit play. Okay, so let's take a look at the solution. This problem is asking us about the probability of the price of a gallon of ice cream being within a particular range between 422 and 485 per gallon. We saw how to find the z-score for those values and then find the area that was trapped in between them. And we did that by finding the table values for each one of those z-scores and then subtracting. And whenever we did that process, we always started with the largest x value first. So our largest x value here is 485. We're going to use the z-score formula, z equals x minus mu over sigma. The x is 485, the mu was 449, and the sigma was 45 cents. So 485 minus 449 is 36 cents over 45 cents, which is 0.80. So that's my first z-score. We also need a z-score for the $4.22. So same z-score formula, but now it's 422 minus 449 over 0.45, which is going to be negative 0.27 over 0.45, which is negative 0.60. We're going to take those z-scores and find their table values. The z-score of 0.80 has a table value of 0.7881, and the z-score of negative 0.60 has a table value of 0.2743. And to find our area in between, and thus our probability, we subtract these values. And 0.7881 minus 0.2743 is 0.5138. So that's the answer to part A, 0.5138. In the second problem, now we're looking at a group of 16. So the first question we wanted to ask is, does the central limit theorem apply? And a lot of times people's answer is no, because they look and they say, oh, there's only 16 in our sample, and we said we wanted 30 or more. Well, that's not quite right, because the way that the conditions worked is you only had to make one of those two conditions true. So the first condition was, if you have a sample of size 30 or more, then you can apply the central limit theorem. We can't use that condition. But the other condition said that if the original population was normally distributed, then it wouldn't matter what the sample size was. You could just use the central limit theorem anyway. And when we read our original problem, it says the cost of a gallon of vanilla ice cream is normally distributed. So that means that the original population was normally distributed, and thus the central limit theorem does apply. So now we have to find our central limit theorem values. Remember that the mu of x bar is equal to mu, and that's 4.49. And sigma of x bar is sigma divided by the square root of n, which is 0.45 over the square root of 16, which is 0.45 over 4 because the square root of 16 is 4, and that gives us 0.1125. We're still going to have to find z-scores for each one of those x values, but now we're looking at x bar equaling 485. Okay? And when x bar is 485, our z-score formula is z equals x bar minus mu of x bar over sigma of x bar. These are central limit theorem versions of the z-score formula. So the x bar is 485, the mu of x bar is 449, and sigma of x bar is 0.1125. If you do the subtraction on top, you get 0.36 divided by 0.1125, and when we divide, we get 3.20. For the second one, if x bar is 4.22, same z-score formula, but then it's 4.22 minus 4.49 over 0.1125, which ends up being negative 0.27 over 0.1125, which is negative 2.40. So we're going to have to look these values up on our standard normal distribution table. When I look up the z-score of 3.20, my table value is 0.9993. When I look up the z equals negative 2.40, the table value is 0.0082. So to find the probability that the average is between 422 and 485, that's the same as finding the probability that the z-score is between negative 2.40 and positive 3.20. We're going to have to subtract these two table values. 0.9993 minus 0.0082, and that gives us 0.9911. So let's interpret, right? There's a 51.38% chance that one randomly chosen gallon of vanilla ice cream will have a price between $4.22 and $4.85. However, there's a 99.11% chance that a group of 16 randomly chosen gallons of vanilla ice cream will have an average price between $4.22 and $4.85. Now, you may be wondering what the difference between this problem and the example problem is. Remember, when we did the example problem about the babies, when we asked a probability for one baby, we were at 34%. And when we asked the probability for a group of babies, we were very, very small, 0.0082. This case is kind of the opposite, where when we asked the probability for one individual, we got a small value, 51.38. And when we asked about the group, we got a much larger probability, 99.11%. So why is it different? Why is it the small one for the group in the example problem, but the large percentage for the group in this problem? And the reason for that is that in this problem, the parameters of our interval, 422 to 485, have the mean inside of it. Right? Remember, the mean for this problem was 449, and 449 is between 422 and 485. Because of that, as we get these more and more members in our sample, that pushes more data values towards the mean, which would push more data values in between the 422 and 485. In the other problem with the babies, the length that we were looking for was bigger than 20.04, and the average was less than 20.04, which was 19.4. So as we got more and more babies, that put more values closer to the 19.4, which actually moved values away from greater than 20.04. Right? So it's the same idea where the values are getting squished in towards the mean. It's just that in the example problem, when it got squished in towards the mean, that made the probability of being far away from the mean lower. Whereas in this problem, because our interval contains the mean, then it's going to contain more and more data values as the n gets bigger. Okay, so that brings us to an end of section 5.4. So please look for your homework on Pearson, and have a great day.